Hi everyone. Today I'm presenting my project on surface chlorophyll A concentrations and what they reveal about primary production in temperate ocean regions. Phytoplankton are microscopic marine organisms that form the base of the marine food web and play a critical role in carbon cycling. Because phytoplankton use chlorophyll A for photosynthesis, scientists commonly use surface chlorophyll A concentrations to measure phytoplankton abundance and overall primary production. In temperate oceans, productivity varies seasonally. Changes in sunlight, nutrient availability, and water column mixing strongly influence when and where phytoplankton blooms occur. Physical processes such as stratification, vertical mixing, and circulation determine how much light and nutrients reach the surface. The goal of this project was to examine how surface chlorophyll A varies over time and across regions, and to relate these patterns to physical and geographic ocean processes. To do this, surface chlorophyll A data from the Ocean Observatories Initiative, or OOI, was analyzed from 3 observatory arrays located in different temperate ocean environments. The Pioneer Array is located in the North Atlantic and represents a temperate coastal shelf system. The Endurance Array is located in the North Pacific and also represents a coastal shelf environment. Separating it from the other two, the Argentine Basin is located in the South Atlantic and represents an open ocean temperate system. These sites were selected because they experience different circulation patterns, nutrient dynamics, and degrees of coastal influence. Surface chlorophyll A concentrations were analyzed over time to identify seasonal trends. Because the measurements were taken at the ocean surface, atmospheric and physical factors such as seasonal light, wind, temperature, and mixing were considered when interpreting the data. The first question to be addressed was how surface chlorophyll A concentrations varied over time. All 3 sites showed clear seasonal cycles. Chlorophyll A concentrations generally peaked in spring or early summer when increasing daylight and nutrient availability promote phytoplankton growth. These peaks represent seasonal phytoplankton blooms. Lower chlorophyll A values occurred during winter when light is limited and during late summer when strong stratification restricts nutrient mixing from deeper waters. These seasonal patterns demonstrate how strongly primary production in temperate oceans is controlled by light availability and nutrient dynamics. Although all 3 sites showed seasonal cycles, the magnitude and strength of chlorophyll A concentrations differed among locations. The Pioneer and Endurance arrays exhibited higher chlorophyll A values and stronger seasonal blooms. Coastal shelf regions tend to be more productive because they receive greater nutrient input and experience more frequent mixing. In contrast, the Argentine Basin showed lower concentrations and weaker seasonal cycles. As an open ocean region, it experiences limited nutrient supply to surface waters and different circulation patterns. These differences highlight the importance of geographic setting in controlling primary production. Beyond seasonal trends, the coastal arrays showed short-term fluctuations in chlorophyll A. These rapid changes likely reflect episodic events such as storms, runoff, or enhanced mixing that temporarily increased nutrient availability. These short-term variations were much less pronounced in the Argentine Basin, reinforcing that coastal systems are more dynamic and responsive than open ocean regions. When considering all results together, several key conclusions emerge. First, proximity to shore strongly influences chlorophyll A patterns. Coastal sites showed higher concentrations and greater variability than the open ocean Argentine basin. One reason is increased nutrient input near shore. In heavily populated coastal areas, runoff and wastewater discharge can introduce nutrients such as nitrogen and phosphorus, enhancing phytoplankton growth and strengthening seasonal blooms. A second influence is physical mixing. Coastal regions experience stronger wind forcing, tides, and wave activity, which can transport nutrients into surface water. Human activities such as shipping and shoreline modification can further alter circulation, contributing to short term variability. A third impact is human stressors. Pollution, sediment runoff, and thermal inputs from coastal cities can affect light penetration and water quality, leading to more complex and less predictable productivity patterns. Despite these findings, several questions remain. One is how continued ocean warming and increased stratification will affect the timing and magnitude of phytoplankton blooms. Another is how increasing coastal nutrient inputs will interact with climate-driven changes, potentially shifting ecosystem toward eutrophic conditions. And finally, it remains unclear how long-term circulation changes will influence productivity in nutrient-limited open ocean regions like the Argentine basin. Overall, this project demonstrates how surface chlorophyll A reflects the close relationship between physical processes, geography, and biological productivity. Long-term observations are essential for understanding both natural variability and future-driven changes by climate and human influence. References are at the bottom. Thank you for watching.